what we're doing today, it's a full day today, so we'll talk about the main pieces of the MRI magnet. That's about 20 minutes, 25 minutes. And then we'll talk about spin versus precession, and a little tiny bit about quantum mechanics. Just the main part. It turns out almost all the equations that we're going to be dealing with later in the quarter don't have any quantum mechanics in it. They're all classical equations basically, so we don't have to worry about quantum mechanics. Just one point about spin and precession. That's a quantum mechanical point. So we'll talk about that today. So let's start off with the main parts of the magnet. So why is it called the magnet? So it's called the magnet because it's a really big magnet. And it's actually, you can think of it sort of like a really big, dangerous refrigerator magnet. And so think about a refrigerator magnet, like when you bring a magnet up to the refrigerator, what happens? Well, pretty much, like here's the refrigerator. It's like nothing, tink. That's the way the magnet is. That's why it's dangerous, actually, because you can actually bring a big, if you look on movies, they do a terrible job of representing the magnetic field. That you always see, like, the magnet turns on and then something starts moving. It's not like that. It's like a refrigerator magnet. So what happens is you can bring a big hunk of metal into the room, and there will be hardly any pull on it. And you get a little closer to the magnet, just a hint, and then you get a little closer, and then it's like 1 ton, like literally 1 ton of force, like just jamming the thing against the magnet. So that's why it's dangerous. And so what causes that? So if you look on the MRI website, there's a nice picture of our magnet before they put all the outer stuff on it. You can sort of see. You can see this big. It's basically a giant. It's just a giant tube. You can see the big stainless steel container. It's like a container that has like a thermos bottle in it. It's a giant thermos bottle. It's like 6 foot tall thermos bottle. And so what causes the magnetic field, the main magnetic field? It's these coils that are completely hidden in the magnet. You can't see them. There's a big bundle of titanium niobium alloy. It's a big bundle of wires, maybe like a couple hundred wires there, and there's just like 4 of them, like that, going. You can't see them. They're completely hidden inside the thermos bottle, and so those things actually are the thing that makes the magnetic field, and that's called the B0 field. So the first part of the magnet, the B0 field. So the B0, so our B0 field is 3 Tesla, and for comparison, the Earth's magnetic field, depending on where you are, it's like 25 to 65 microtesla. So that's a millionth of a Tesla. So this is, 10,000 times stronger than the Earth's magnetic field. So you're in the Earth's magnetic field all the time. Doesn't really do anything obvious unless you have a compass needle. But it's considerably stronger than. So that's this is the Earth, because the Earth is also a magnet. Okay, so how does that work? So basically what happens is there's charges, they're electrons, but you can think of them as, positive or minus and flip the sign. But they basically, these things are, I'll do it on this one so we don't get in the way of the other illustration. So basically, if these guys, say, which way did I have them going? I'm going, let's just make them go that way. Is that the right way? No, let's make them go up. Okay. So these charges are moving around there, and there's a rule called the right-hand rule. And since this is being mirror flipped, I have to use my left hand, which looks like my right hand. And what the right-hand rule is the direction of your thumb is the direction the charges are moving. And then the direction of your fingertips is the direction that the magnetic field that's created. So in this case, what happens is if the charges are going around the wire that way, it's going to make the magnetic field, point in that direction. So that's how you figure out, that's a handy rule to sort of figure out if you move a charge, what is the direction of the magnetic field. So the magnetic field it's not just a number, it's actually a vector because it points in a particular direction. It can point in all different directions. It can have different amounts of strength, but it can also point in different directions. So it's a vector. And so your fingertips will tell you what direction the vector is. And this thing we'll call the J vector. That's the direction that the charges are moving, that's the direction of the current. So how does this current get in there? Well, like almost 100 years ago, physicists figured out if you take a wire, certain kinds of wires, and make them really cold, the resistance to current flow disappears. Now, they already knew, before they made them super cold, they already knew that the resistance got lower. So what is resistance? It's like a toaster. Like when you run current through the wires in a toaster, they get hot. That's like resistance to current flow. So if you cool the toaster down to like 70, minus 70, and run current through it, there will be less resistance. But if you get it really cold, like a couple degrees above absolute zero, which is about like minus 450 degrees in Fahrenheit, the resistance doesn't just get low, it just drops to zero. So it's going down, 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 and then it just goes zero. And so what that means is if you put a current in a wire, it just keeps going around. And it's just like magic, So you have to make some connection or use a transformer or something to sort of induce the current in these wires. But once you've got it in there, it's just going around and around and around and around. It takes a couple hours to turn it all the way on. And then it's not plugged in. It's just the most amazing thing. So it's not plugged in. It just like goes around and around and around and around. And it makes a huge magnetic field. And that magnetic field is called the B0 field. And it's pointing in this direction. So this is the B0 field. And that's a vector because it's the same everywhere inside here. So no matter what part of the inside of the magnet you go to, you've got a vector of the magnetic field that's the same length. So think of it's like look into the 3D space inside the magnet and imagine like at each point there's an arrow, and that arrow is the same length. And it's pointing in that direction because the positive current is going around that way. Yeah. Okay, so that's the first thing. So that's always on, it's not plugged in. So like when the power went off, lights all went off, magnet's still on. It's kind of dangerous. Nothing is on, no warning lights, nothing. It's still on. So our magnet has not been plugged in since 2017. So the current's just been going around the whole time. It's truly amazing. Okay, so that's the B0 field. So then we have the gradient coils. So the gradient coils also affect the B0 field. And so now we have to sort of mess up our diagram a little bit. So now we've got some gradient coils in there. So the gradient, you can't see them either. It's just another big cylinder of epoxy and wire. It weighs about 2 tons. They had to take it out at one point. Made a big dent in the floor. So this is the gradient coil, and this is the part that makes noise. So this part is actually Let's label this. So here's the B0. So that's that guy. And the gradient coils are this guy. So what's the point of the gradient coils? So the point of the gradient coils is to modulate the Z component. This is, so, modify, just say, not modulate, we'll just say modify Z component of B0. So I said coils, so why do you need 3 of them? So basically you can modify the Z component of the B field in the X direction, or you can modify the Z component of the B field in the Y direction, or modify the Z component of the B field in the Z direction. So we didn't make our little coordinate system, but here's our coordinate system that we're going to be using. So that direction coming out of the magnet, that's the Z direction, and then going up, we'll call that the Y direction. So that's the Z direction, and then coming out at you, and that's the X direction. So we're going to use this coordinate system for the rest of the quarter, so semester. And so what does something like the X gradient do? So if you've got somebody in the magnet, so to illustrate the X gradient, we have to sort of look from the top. So let's imagine you got somebody in the magnet. So here's happy person in the magnet, smiling. Scan me harder. Okay. So what is the Z the X gradient do? So that's the X direction. Left, right is the X direction. So you start off with the B0 being the same everywhere. So no matter where you go, I'm only drawing the arrows that belong to a line, but at every point in 3D space, the magnetic field is pointing in that direction, like that. And so what the Z gradient does is it just adds a little bit or subtracts a little bit along a line. So it's not anywhere near as powerful as the B0. It's maybe like 1/500th or 1/50th, something like that. 1/50th as powerful as the main field. And so I'm exaggerating how big the difference is, but what it will do is it will say you turn it on this direction, it will add to this depending on where you are in the X direction, because this is the X direction. And so when you get to the middle, it's not doing anything, and then it subtracts a little bit like this. So that's like the X gradient. So it's not changing the magnetic field in the X direction. It's not sort of changing the direction of the magnetic field toward X. What it's doing is it's changing the Z amount, the horizontal amount of the magnetic field as you move in the X direction. And so it's clear you could have 3 of those. So you could change the magnetic field as you move in the X direction, change the Z as you move in the X, Z as you move in the Y, Z as you move in the Z. So that's the gradients. And so why do they make noise? Well, they've got 3 1.5 million watt amplifiers attached to them. So these are like giant stadium sound amplifiers that are attached to these. So I didn't draw anything in the coil. There's a bunch of wires in the coil to make these gradient fields, and they're rapidly changing back and forth. So what might happen is you might, like every 100th of a second, you might flip the gradient back and forth to sort of like making the right side of the guy's face slightly smaller, to making the right side of the guy's face a little bit bigger. And so it's kind of like a speaker, because you can sort of, like, how does a speaker work? You run current through the coil in a speaker and it moves the coil, makes noise. Well, this is like a 4.5 million watt amplifier, stereo amplifier, 3-channel amplifier hooked up to, and then it's sitting inside a giant speaker magnet. And so the physicists work a lot to try to make it not make any noise. But as soon as you power up like the million watt amplifiers, what's going to happen is it will make the gradient coils make a magnetic field. That magnetic field will interact with the magnetic field. It will be in a different direction of the B0 field, and it will try to move the gradient coil a little bit. And then when you flip it the other way, it'll try to move it the other way. And so the gradient, this giant 2-ton gradient coil is going, that's what the noise coming out of the magnet actually is. Okay, so that's the gradient coil. So any questions about the gradient coil so far? All good? We haven't said what they're for, but that's we'll get to that. Okay, so then we got so we haven't made any signal. So now we need the body RF coil. And RF stands for radio frequency. But this is yet another coil. Make it in a slightly different color. This one basically sort of forms the inside of the bore. So if you pull the sort of tube that you're sitting inside out, the RF coil is attached to that. So that's another coil in there. And what this one does, so this guy is body RF. So this guy is right there. So this one also makes a magnetic field, yet another magnetic field. So what is radio frequency, like radio waves? Those are disturbances in the magnetic and the electric field that are propagating through space. They can go through empty space. So we didn't say anything about the electric field. Electric field would be like static electricity. But here we're just interested in the magnetic field part of it. And because radio waves have magnetic fields in them as well. And so what the RF coil does is it causes a rapidly rotating magnetic field to occur. So what does that look like? So that looks like, so I'll draw it out here. So here's the B0 field, but now you can imagine, I'm exaggerating it, the effect isn't as big, but in order to be able to see it, let's make it bigger like that. Okay, so what the RF coil does is it makes a rapidly rotating magnetic field somewhere along this circle, and it's rapidly rotating. Let me draw it down a little bit so I can annotate it a little easier. So say it's going this direction, and say it's rotating that way. Okay, so that thing is called the B1 field. So remember the B0 field, the charges are moving around, but the B0 field is static. It's just pointing in one direction. The B1 field is very rapidly moving. So it's moving, for our magnet, it's moving like 123 megahertz. So that means 123 million rotations per second. So that's like an FM, it's pretty much like an FM radio station, same frequency. It's much lower frequency than your cell phone. Your cell phone is like 1 or 2 gigahertz. That's a billion cycles per second. This is like, 100 million cycles per second. So that's called the B1 field. And so what that does is this coil does that. It causes this rapidly rotating magnetic field to sort of rotate around perpendicular to the B0 field. Now, this is just kind of a conceptual, sort of a conceptual convenience. There's only one field, this field right here, which is the vector sum of those guys. That's just the B field. So there's really only, at any point in space, there's just one magnetic field, but we've conceptually broken it up into a field that comes from the RF, a magnetic field that comes from the RF coil and rotates perpendicular to the B0 field, and then a stationary B0 field. So what's the bottom line? The bottom line is you've got the total B field without B1 or B0 is just wiggling around. It's just kind of rapidly wiggling around. Okay, so you need that. You need that in order to make your brain generate a signal. So that's the thing that essentially sweeps up the protons and sort of gets them all lined up with each other, so that when you turn it off, you can actually get a little radio wave to come out of your head. Okay, so that's the body RF. So we did, the B0 coils, the gradient, body RF, and then finally we have to pick up the signal. And so this is, in modern magnets, this is done by receive only RF coil. So we need a person in here. So there's a ugly MRI Marty person in there. Okay, there they are. Okay, so we need yet another coil, and make that one green. So here's a coil that's sitting there, and there's another. I'll put another. There's there could be like 30 or 60 of these guys. So those are some coils that we have right next to the person's head, and they're designed to pick up the radio signal that comes out of the head after we've done the body RF signal to essentially sweep all the protons into alignment with each other. So this guy is that one right there. So that's the body RF coil. So that's what picks up our signal. Picks it up from the whole head, pretty much. And then last but not least, there's some shim coils. And these, whenever you stick something in the magnetic field that's not completely uniform, like if you filled it all up with gelatin, the entire bore with gelatin, that wouldn't disturb the magnetic field. But if you put a person in there, they've got like a body on one side and no body on the other side. And so that's going to actually cause the magnetic field to get a little bit non-uniform. And so the shim coils, there's a whole bunch of shim coils that are designed to sort of cancel out the disturbance in the magnetic field caused by putting something into the magnetic field. They're actually in the gradient coils. So we'll put these guys inside the gradient coils. That's where they are. Okay, so that's pretty much it. So everybody's good on all the parts. So we just got this B0 field. This is necessary to polarize the protons. We'll find out. And then we got the gradient coils. That's how you make the images. Those guys change the strength of the B0 field and the Z component in different directions. And then you got the body RF, which is making a magnetic field that's perpendicular to the B0 field that's rapidly rotating around. It adds on to the B0 field. And then you got to pick up the signal after you've generated that signal. Okay, all good? Parts of the magnet. Okay, so now I have to talk about quantum mechanics just for like about 10 minutes. So quantum mechanics, you think of quantum mechanics as advanced, but the Greeks kind of knew about quantum mechanics. They already knew that if you go drill down really deep, everything's made out of atoms that are all the same size. They're sort of quantized. Their weight is quantized, and chemists figured this out long before the quantum mechanical physicists came up with theories for it. So you can just tell from doing chemical experiments that, like calcium, it's all exactly the same size. It all weighs exactly the same amount. The mass is quantized. So if you look at quantum mechanics, It's this very strange theory. And it works really well, but if you ask most physicists, they don't particularly like it. Because it's just so bizarre. So we'll just talk about 1 minute of quantum mechanics and then an actual experiment, a basic experiment that's related to this spin and precession. So how does quantum mechanics work? Well, you've got a differential equation, wave, it's called a wave equation, very similar, not exactly the same, but similar to the equations you use for describing like radio waves, classical radio waves. And so that guy is the Schrödinger equation. Okay, so then you solve that equation. So what does that do? That just says for some function, usually with that sort of little wavy, dangerous looking symbol, this is what this function is going to do a tiny bit of time into the future, or a tiny bit of space off to the right. So like you're at a point in space, and what the Schrödinger equation says is the value of this psi function, if you go a tiny bit off to the right or a tiny bit forward in time, is going to be such and such. So that's the differential equation. So you solve it, so you get a solution to it, and the solution basically, over space and time. And we'll do a very simple example of this when we talk about the Bloch equation. We're not going to talk about the wave equation solution. But basically, you get a solution that's over space and time. But what's the part about this that the physicists, like Einstein hated quantum mechanics. Schrödinger didn't like quantum mechanics. He invented it. He kind of like got out of it in his later years. And the part that he didn't like was the part. So let's just imagine we've got, like, say, the x position. So we've started off the world in some state, and we've solved the Schrödinger equation, and say we get something that, that looks like that. Now the first problem is the solution is complex. So at each point here, you've got like a real and an imaginary part. So you got two numbers. You got two numbers at each point in space and time. So that's kind of weird. Like the world is real. Like, what are we going to do with that? And so what the physicists do is they square this. So if you square that, you get rid of the complex part. You get rid of the imaginary part, because I is the square root of -1, and if you multiply that, two i's times each other, you just get -1. So you get rid of the I. So you square that, and then you call that a probability of, say, the particle being in a particular place. So this is like you say after we square this guy, we can say there's a pretty good chance the particle is over here. And it's a higher chance it's over here. Okay, it's all good. And then we make a measurement. And that's the part that's kind of just totally bizarre. So we take a measurement. And so what is a measurement? Oh, well, a measurement is we put a screen up, and maybe the particle slams into the screen, and we can see a little spot. And so then we say, the particle's right here. I know it's exactly right here. So the Schrödinger equation didn't do that. Like God made a measurement and just said, like, that's where it is. We now know it's here. And so then what do? You put that into the Schrödinger equation and run it. And what happens is, well, it starts to spread out again, into waves. So that's the part that all physicists don't like. It's just this uncomfortable thing. Like, you do a measurement, and the measurement isn't really part of the dynamics of the Schrödinger equation, and then you say, like, it's actually there, and then we crank the Schrödinger equation, and it spreads out into probability waves. So Okay, so maybe that will stimulate you to read more about quantum mechanics, or maybe not. I read it sometimes late at night, puts me to sleep in about 1 minute. So that's all about quantum mechanics. But what's an actual concrete experiment that's related to MRI? And this was an experiment done early in the days of quantum mechanics called the Stern-Gerlach experiment. It's a basic experiment. And how does this work? You get something, you get some atoms that are not charged. You don't want ions, you just want atoms. So like neutral silver atoms. So neutral, and then just shoot them through. So accelerate them somehow, and shoot them through a magnet. And so here's a big magnet. This guy's a big magnet. Now, and this is one of the things that really gave people the idea that there's something like spin. So why do we call it, spin in the first place? Well, imagine classically we've got like a little ball of something, like a little atom, and imagine it's got a charge on it. So say there's a charge on it, and say that charge is just sort of spinning around. What is that going to do? Well, it's going to be the, so if the, how can I do it? Yeah, there, I got it up. Okay, so if the charge is rotating around like that, what's going to happen is it's going to make a magnetic field sticking up out of the little spinning ball, like a little refrigerator magnet. Because when you move a charge, it makes a magnetic field. And so basically atoms act as if they were spinning, and they had these little magnetic fields associated with them, in addition to their electric charge, like static electricity type charge. So what happens is if you shoot these atoms through here, what would you expect? You'd expect these little magnets here of the, this is, like you can imagine, this is a current, like a current moving around the surface of that little ball, and then there's the magnetic field that current makes. You'd expect they'd be all in different directions here, because they're not polarized in any way. And as they went through the magnetic field, you'd expect them to sort of spray out into all different directions. But what happens? What happens is you just get two. So if you put a screen there and sort of measure where they're hitting, you just get two. Just get two beams. So basically what happens is somehow the atoms, when they run through this magnet, they just sort of flip in one direction or flip in another direction, but there's basically nothing in between. So that's the basic physical observation. You take some atoms, run them through a magnet, and you get something you weren't expecting, which is that they just split into two beams, and instead of just splitting into like a whole bunch of different beams. So somehow when they go into the magnet, they have this weird quantum behavior where they sort of either flip in a direction opposite to the magnet, or flip in the direction lined up with the magnet. And it's just an empirical thing. You could just do this with atoms. This is just what they do. So with that in mind, let's look at the microscopic sort of quantum mechanical picture and macroscopic picture, which is the only one that we're going to be concerned with for the whole rest of the quarter. And so what does that look like? And then try to relate it to a top. So let's make a nice big diagram over here. So we got six cells in our diagram. So here's the microscopic sort of quantum picture. And here's the macroscopic. So this is our QM picture. And we're going to do three different conditions. So the first condition, we've got no B0 field. And then the second condition, we have a B0 field. And then the third condition, we've also turned on the body RF coil. So that's the three conditions. So we'll start off with no strong B field. So if there's no strong B field, these guys are still spinning. They're always, they're quantum. They're always the same weight. They always have the same amount of spin. They always have the same little refrigerator magnet. And so all those refrigerator magnets are pointing in different directions. So they're all, if you just have like a piece of gelatin or whatever, a piece of brain, they're just all pointing in random. They're all the same length, but they're just pointing in random directions. And there's quite a bit of, if they were all pointing in the same direction, you'd have a really strong magnet, but they're just all pointing in random directions, so they all cancel each other out. And so when you add them all up, imagine like each little magnet's pointing in all different directions throughout this 3D volume, add them all up tip to tail. What do you end up with? You end up with 0. And so here's like the voxel picture. So are macroscopic. So you can see these are little voxels, for example, 1 millimeter. And so if you add up all the magnetic fields, they're all pointing in different directions and they all cancel each other out, so you get nothing. So there's magnetic fields in your tissue, but they're all canceled out to nothing. So now what happens when we turn the B0 field on? And just for the time being, I'm going to make the B0 field go up, because this is the way the diagrams are usually made, instead of sideways, because in the magnet, the B0 field is, parallel to the floor, but here we're just going to make it go up. So here's the B0 field. So that's the B0 vector. So now what happens? So now weird quantum things happen. And so we can draw this by two little cones like that. So what happens is when you go into the magnet, it takes like about a full second for this to happen. You get slightly magnetized. So you get slightly magnetized. And what does that mean? Well, it means that there's slightly more of your little proton magnets pointing in the up direction than there are in the down direction. And it's not very much. It's like maybe a couple parts per million. So a couple parts, so you're a terrible magnet. So it's just a couple parts per million more in the up direction than in the down direction. But there's this funky thing going on, is that the angle that the magnets assume, like in the Stern-Gerlach experiment, is either 54.4 degrees this way or 54.4 degrees this way. So they refuse to line up with the magnetic field. They're always going to be off. They're always going to be off from the magnetic field by 54 degrees. We can just actually measure this. And there'll be slightly more of them pointing up than down because of this very strong magnetic field. Now, I know all this just seems completely unreasonable, but if we add that all up, what happens? Well, so you can sort of think of these guys as, they're already precessing. So you can think of them, they're already kind of precessing around the main magnetic field like a top would. But they're not lined up with each other. And because they're not lined up with each other, the XY components all cancel out. And so if we add up, if we sort of zoom out to the macroscopic level, add up all those vectors, there's slightly more of them pointing down, so slightly more of them pointing up. Let's make a couple extra here so it seems like there's more pointing up, even though it's like only a couple parts per million. There's slightly more pointing up than there are pointing down, but they're evenly distributed around the circle, and so all that part cancels out, and what do you end up with? You end up with each little chunk of tissue magnetized in the direction of the magnetic field. So that's the B0 on. Okay, then last but not least, we have to turn on the B1 also. So add B1. So the B0 field was static, but the B1 field was rapidly rotating around. So add this B1 field that's rapidly rotating around in the XY plane. So now what happens is you can sort of think of what happens as you kind of bunch these guys up. So what happens is you get them a little sort of more bunched up in this direction at any one moment in time, because this thing is rapidly going around. And then there's less of them sort of in other directions like that. And there'll be, a few more pointing in the up direction. And so what happens if we add all those up? So if we add all those up, what's going to happen is you'll get a vector, that's, if this was the horizontal plane, it'll be sticking out of the horizontal plane a little bit like that. It'll be, slightly up out of the horizontal plane. Rapidly rotating around, because we kind of swept them all into alignment with each other. And so what happens if we look at one of these voxels? So if you look at one of these voxels over time, that magnetic field vector will now be rotating around. So here's like, several time points of just one of these guys. So let's just like blow up one of these guys. So now what's going to happen is that vector is going to be, at different points in time, it's going to be sort of like, rapidly rotating around like that. That will make a signal. So when you rapidly change a magnetic field, that is going to make a signal that we can pick up with a coil. When you rapidly change a magnetic field, it causes a current to flow in a coil. So it's exactly the reverse of generating a magnetic field. So if you move a current in a coil, it makes a magnetic field. If you rapidly change a magnetic field, it causes a current in a coil. And so that's the fundamental signal that we record. But the way we're going to think about it for the rest, this doesn't sort of make much sense, but the way we're going to think about it for the rest of the semester is, you just, at any one point in time, at one point in the brain, you've got a magnetic field that's pointing in a certain direction. It's just like a classical refrigerator magnet. We don't have to worry about the quantum stuff. Okay, so that's, so how does this relate to, finally, how does this relate to a top? Because, we said, you can think of these guys as, already precessing, but since they're all uniformly distributed around this 54-degree offset around the circle, you don't get any bulk signal out of it, because they're all sort of canceling each other out. So here's sort of their aligned precessing. So what I said at the very beginning was that quantum mechanics is actually easier. It's actually easier. And so the first equation, the first basic equation of the class is the equation that describes the precession frequency. And that equation is 2 pi times the precession frequency, which is equal to omega. I'll tell you what that is in a second. So that's a frequency. Both of these are frequencies. And what is that equal to? That's equal to a constant. This guy gamma is a constant times the strength of the B0 field. So here's the B0 field vector. And if we put those things, that means like get the length So get the length of the B0 vector. And then what is this thing? Well, this thing is the precession frequency, which means not the spinning frequency, it means like with a top, where you have a top spinning around its axis, that's the spin. But then if you spin a top and put it on the floor, it starts to precess and sort of go around, and it's still spinning around its axis very rapidly, but then it's much more slowly precessing around, just the way like a physical top on the floor would. And that's the precession frequency. And what's that symbol there? It just means radians per second. And what does radians mean? Radians just means it's an angle that is, if you have a circle of radius 1, it's the angle by going 1 along the circumference. So it's that angle. So it's a circle. The radius of the circle is 1. If you go 1 radius along the circumference of that angle, that's 1 radian. And so in physics, you constantly go back and forth between these guys. So why do we need the 2 pi there? Well, there's 2 pi, a little over 6 radians going around a circle. So sometimes you have the 2 pi. So this guy, what is this one? This is also the precession frequency. But this one is, the precession freak in cycles per second. So a cycle meaning like going all the way around the circle. So that's why I always end up sort of messing with the 2 pi business. But look at how easy this equation is. This equation is incredibly easy. It's way easier than a top. So what it says is, so this guy's a constant. So this one's the gyromagnetic ratio. That's constant. It's constant for a particular kind of an atom. So this is an incredibly simple equation. It just says that the frequency that this precession occurs at, which is kind of already occurring here, but you can't see it. So this precession frequency is just proportional to the B0 field. So you up the B0 field, you up the precession frequency. Simple as that. So that's an extremely simple equation. And all MRI is based on that. We're sort of like changing the B0 field and we're messing around with the precession frequency. Okay, so we instantly change the precession frequency if we change the B0 field. Now, just to sort of compare that to a top. So here's a top. So a top is much more complicated because, it can be all different sizes. So say here's a top, and say the top, consists of like a little chunk of metal like that. But now we've got several things like how long is the stalk of the top, and how is the metal? What's the that symbol is just like how is the metal distributed in the top? Is it like a long thin disk or is it a shorter disk? That's going to change things. So what's the equivalent equation for a top? So we said that these protons act like tops, like precessing tops. They act like they're spinning around their axis invisibly and then much more slowly moving around the B0 direction. So what's the equivalent equation for a top? So here's the frequency of the top precession. Can't spell precession, yeah. There we go, much better. So the frequency of the top precession, it's more complicated. It equals, well, how long is the stalk of the top? How much does the top weigh? We've got to consider like, a bigger, heavier top is going to precess at a different amount of mass. And then here's how much gravity there is. And the gravity is kind of like the B0. But then it's divided by, the moment of inertia, like how is the top mass spread out? Is it like a long top or a small top? That's going to be different. And then finally, under here is the top can be spinning at different different speeds. So this is the top, spin frequency. So this is the top precession frequency, which is the thing that's like, it's like this one. It's like what is the precession frequency of the top. So you can see the top is much more complicated. Now when you see an equation like this is I put this up here for a reason. The first thing you have to do is it's a little machine, so operate the machine. So let's just operate it quickly here. So the top precession frequency, how is it affected by the stalk length? So if you make a longer stalk length, what's going to happen? It's going to increase the top precession frequency. What if we make a heavier top? It will increase the precession frequency. What if we turn gravity up? That's a little harder to do. We could go to the moon or turn gravity. So if we change gravity, higher precession frequency. What about this moment of inertia? What if we sort of spread the top out, make a bigger moment of inertia? That's in the denominator, and so that's actually going to slow the precession frequency. That's kind of like a figure, like a skater. Like if you bring your mass in, you spin faster. So that will actually, or if you run your mass out, like move your arms out, you'll spin slower because it's in the denominator. And then the speed that you spin the top, if you spin the top faster, what happens? Well, it's in the denominator, so that means that the precession goes slower. So you can see it's a much more complicated thing. But what you can think of, you can sort of like imagine like these guys, all these four numbers here, are all constant with the atoms. And so they're pretty much just like this guy. And then, gravity is like the B0. Gravity has a direction too, but we can just consider like how strong the gravity is at a point. That's what we're doing here. So that's the same as that. So you can see a top is much harder. So quantum mechanics, because everything has the same spin, it all weighs the same, and it's all in the it's all the same shape. Everything's much easier, and so we have a much easier equation here, which is that the precession frequency is just proportional to the magnetic field. Period. And we're all done. Okay. So is everybody happy with quantum mechanics and tops? There's got to be a question or two. I kind of barreled forward without giving you much chance for questions. So any questions about this picture that we have these little tiny magnets, and they've got this strange property that when you put them in a magnetic field, they sort of pop into two orientations. And then we can add some radio waves into it and kind of sweep them so that they're all precessing together. But they've got this strange angles going on. But if we just add them all up, we just end up with a single vector. We call this one like the bulk, magnetization, because we're kind of ignoring all the, this is the bulk magnetization. So we can treat it as if it was just like a little refrigerator magnet pointing in a certain direction at any one moment in time. And that's what we're going to do for the rest of the semester. Okay. Everybody happy with this so far? Sort of. And simple equation. Boy, I mean, this one's much more complicated. Very simple equation. It's just proportional to the precession frequency is proportional. You can either do it cycles per second or radians per second, which is, question? Yeah. So what's the difference between these two cases? So what you can think in this case, they're precessing, but they're all kind of like out of sync with each other. So if they're all out of sync with each other, then you end up with, you essentially cancel out any sort of difference along these two directions here, like, yeah. Yeah, they're just sort of like they're polarized, so there's slightly more of them, pointing aligned with the field, but we call that the phase, that like where they are along the circle is just completely randomized, and so that all cancels out and we just end up with one going vertical. And then if we start to sort of sweep them together, we can have varying amounts of signal that actually comes out in this XY plane. And that's what our whole sort of MRI signal is based on. Okay. Any final questions? So Friday we talk about, because we're going to be talking about dot product and cross product, we'll slowly go over dot product, cross product, and complex multiplication. So we can sort of, because we need to, we have to go over these to understand the later equations. They're relatively simple. It's got maybe 10, 20 parts, something like that, not too many parts.